Hello everyone, welcome back to the course Vector Calculus and Complex Analysis. Myself Dr. Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. In the last session, I have introduced the Cauchy's integral formula and we have solved some problems, or we have discussed some problems on Cauchy's integral formula. Today also I am going to continue the same. We will evaluate the line integral of a function along a curve C using Cauchy's integral theorem as well as Cauchy's integral formula. So when we apply the theorem, when we apply the formula that already we have discussed in the last session, again I am going to repeat the same now. If the singular point z equal to a lies outside the circle, apply Cauchy's integral theorem. If it lies inside the circle, then Cauchy's integral formula. So outside C, inside C. So first we need to identify the singular points and then we check whether those singular points lies inside or outside. Sometimes one singular point may lie outside and the other singular point may lie inside the curve. So according to that we apply the theorem. Now what is the Cauchy's integral formula? If f is analytic everywhere on and within a closed curve, but at a point z equal to a it is not analytic, it fails to be analytic or fails to have derivative, then we can find the line integral of a function which is in the form of f of z by z minus a dz using this Cauchy's integral formula, and the result is 2 pi I into f of a. So if this is the singular point, this singular point lies inside the circle or inside the curve, given curve, then the result of this line integral is 2 pi I into f of a. For example, if this singular point lies outside the circle, then simply the answer is 0. That is Cauchy's integral theorem. Now let us solve one problem. Evaluate the line integral where C is the circle mod z equal to 3. So given line integral f of z by z minus a dz, this is in the form of e power z by z minus 1 z minus 2 dz. Here of course this is f of z, so f of z is e power z, but the denominator z minus 1 into z minus 2, we need to split this using partial fractions. You know how to find the partial fractions: a by z minus 1 plus b by z minus 2, and by finding the LCM, here 1 equal to a into z minus 2 plus b into z minus 1. Now we need to eliminate one of these two constants. So put z equal to 2 so that this a will be eliminated, z equal to 2 so b equal to 1. Similarly put z equal to 1 so that b will be eliminated, then 1 minus 2 so a equal to minus 1. Therefore this is 1 by z minus 2 minus 1 by z minus 1. So this will be rewritten as e power z by z minus 2 minus e power z by z minus 1 dz. So split this into two parts: e power z by z minus 2 dz minus e power z by z minus 1 dz. So therefore the given line integral is the combination of two line integrals. Now what is the curve C? Given C is mod z equal to 3. This is mod z equal to 3 is a circle with center at origin and radius equal to 3. So coming to the first part, the line integral along C e power z by z minus 2 dz, where C is mod z equal to 3. Clearly, z equal to 2. Here z equal to 2 is a singular point. I told you, first we need to identify the singular points by equating the denominator to 0, z minus 2 equal to 0. So, z equal to 2, that is a singular point that lies inside mod z equal to 3, because here the radius is 3 and here the value is 2 itself. So, obviously it lies inside that circle. Therefore, by Cauchy's integral formula, the line integral f of z by z minus a dz is 2 pi I into f of a. So, e power z by z minus 2 dz is 2 pi I into f of 2, z equal to 2, and 2 pi I into f of z is e power z. So, put z equal to 2, e power 2, e square. Similarly, the second one, the line integral along C e power z by z minus 1. Here again the singular point is z equal to 1 lies inside mod z equal to 3. So, in both cases z equal to 1 and 2 both lies inside the circle. Therefore, by Cauchy's integral formula, e power z by z minus 1 dz, the answer is 2 pi I into f of a, 2 pi I into f of 1. So, 2 pi I into e power 1. So, in both cases we have evaluated the line integral. Hence, the line integral C e power z by z minus 1 into z minus 2 dz is 2 pi I e square minus 2 pi I e. So, 2 pi I into e square minus e. Now, coming to the next problem, line integral along C e power z by z minus 1 into z minus 4 dz, where C is the circle mod z equal to 2. So, here again the given integral is e power z by z minus 1 into z minus 4 dz. First, we need to split this into partial fractions. So, by splitting this into partial fractions, we get 1 by 3 into 1 by z minus 4 minus 1 by z minus 1. So, therefore, this line integral e power z by z minus 1 into z minus 4 dz is equal to 1 by 3 into the line integral e power z by z minus 4 dz minus e power z by z minus 1 dz. So, again we need to evaluate two line integrals along the given curve C. And what is the curve here? C equal to mod z equal to 2. And here in the first one, so C is mod z equal to 2. First one, the line integral along C e power z by z minus 4 dz. Here z equal to 4 is a singular point that lies inside z equal to 4. Here the radius is 2 itself. So, lies outside mod z equal to 2. Therefore, by Cauchy's integral theorem, the line integral f of z dz is 0, since the point lies outside the circle. E power z by z minus 4 dz along the curve is 0. And second point, second problem, e power z by z minus 1, e power z by z minus 1 dz. Here z equal to 1 is a singular point. By equating the denominator, we get that z equal to 1, which lies inside the circle mod z equal to 2. Here the radius is 2 and z equal to 1 is the singular point. Obviously, it lies inside the circle. Therefore, by Cauchy's integral formula, the line integral f of z by z minus a dz is 2 pi I into f of a. So here the line integral e power z by z minus 1 dz 2 pi I into f of 1. And what is f of z here? E power z. F of 1 is e. So 2 pi I into e. Hence, the line integral e power z by z minus 1 into z minus 4 dz is equal to 1 by 3 into the line integral e power z by z minus 4 first, then minus z minus 1 e power z by z minus 1 dz. So this is equal to 1 by 3 into, here we got 0, for the second one 2 pi I e. So minus 2 pi I by 3 e. So like this we can evaluate the line integrals along the given curve using Cauchy's integral theorem as well as integral formula. So in today's session, I have solved some problems. On Cauchy's integral theorem as well as Cauchy's integral formula. So this is for today's session, and we will meet in the next session. Thank you.